The limit as x approaches 0 of sine of x over x. We know that if we plug in x, we'd get an undefined denominator. So if we take a look at a graph of the function, here's what it will look like. We can see that the sine of x over x is going to approach a limit of 1 as we approach from the left, and a limit of 1 as we approach from the right. So our limit is going to be equal to 1. Likewise, if we graph the cosine of x minus 1 over x, you'll find graphically that the limit will approach a value of 0. Let's take a look at x cubed minus 2 divided by x minus 3 graphically. If we take a look at the graph, we can see that as x approaches 3, from the left is going to be a different value because we're approaching a asymptote at 3 from the limit from the right. There is no function from the right. Therefore, we would have to say on this one that the limit does not exist. Moving on, if we're going to find a limit as x approaches a value, we're going to simply plug that value into the function to find our corresponding y value. So if I take the limit of this one, 4 times 5 squared minus 2 times 5 plus 6, we'd have 25 times 4, 100, minus 10 plus 6. 96. Just another example to show graphically. We're looking for the limit as x approaches 0. We can see from the left and from the right we're approaching a value of 1, so the limit in value is 1. Here's just another example. On this one, the limit as x approaches 0 from the left will go towards negative infinity. The limit from the right goes towards positive infinity. So since the limit from the left does not equal the same thing as the limit from the right, there is no limit. So the limit does not exist. Okay. Here's what we look at in the structure of how things are written. So I'll write it a little bigger because it's hard to read. The right-hand limit is limit as x approaches some number from the right, as a little plus with it, and then from the left is x approaches a number, has a little, what looks like a little negative sign with it, so this is from the right, and this is from the left. So we say that if the left and right hand limits are equal to each other, that will be equal to the limit as x approaches that value. So we always look at from the left and from the right to see if they match. So here's some examples to take a look at. The limit as x approaches 0 from the right, so we look at 0 from the right would equal 0. The limit as x approaches 2 from the right, so we're approaching 2 from the right, there is no value because it ends at 3. We're approaching 2 from the right, so that one does not exist. Limit as x approaches 2 from the left, we're up at 4. Therefore, since the left and right hand limits as we approach 2 are different, it does not exist. The limit as x approaches 3 from the right is going to be 0. Here's another example. The limit as x approaches, we'll start with over on the right side down here, 3 from the left is equal to 1. The limit as x approaches 3 from the right is equal to 1, so that limit is 1. The limit as x approaches negative 4 from the right is equal to 2. The limit as x approaches negative 4 from the left is 2, so that's the limit as x approaches negative 4. But at negative 4, we're at 0. The limit as x approaches 1, we can say we have to look at from the left and from the right. So as we're approaching 1, along the x, we can see from the left and the right, we're at negative 3. So that would be our limit, since it's the same from the left and the right. If when you plug in the number, it initially doesn't work, and it doesn't look like graphically, it does look graphically like it might work, we can use two different methods to help us figure out our answer. The first is factoring. Check to see if the numerator factors in this problem. And if it has a common factor, then whatever's left will plug in negative 1 into the numerator that's left. This means that there's not an asymptote line there. This would mean that there's simply a hole in the graph there. So if we take a look at this one, we have x minus 4, x plus 1. The x plus 1 cancels. Now we plug in negative 1 minus 4 equals negative 5. On the second one, we use what's called the conjugate method. The conjugate is the same factor in the numerator with the other sign of its conjugate. So this would be negative 2, we'd have plus 2. If it were plus 2, this piece would be minus 2. We have to multiply both the top and bottom by this value. It's called its conjugate. Because we notice when we plug 7 in to the denominator, again, it would just be undefined. So we're going to try the conjugate method. It looks a little bit scary, but it's not too difficult. We don't have to simplify the denominator necessarily to help us to figure this out. So we're going to FOIL. When we multiply a square root times a square root, the square roots cancel. Because we chose a conjugate, the outside and the inside terms are going to cancel each other out automatically. So then we're just left with negative 2 times 2, negative 4. And that would equal x minus 7, same as the denominator piece of the first piece. Again, we don't need to simplify this second piece of the denominator. So we can see that these will cancel. There's a 1 left in the numerator. Now I can plug in 7. 7 minus 3 is 4. Square root of 4 is 2 plus 2 is 4. So I'm left with 1 in the numerator and 4 in the denominator. So my answer is 1/4. Just real briefly, the sandwich theorem allows us to take a look at if we have a function that f and g or g and h or whatever the two functions are, and they have the same limit as x approaches a value, then that would have that limit as well. Where this comes in handy is if we have functions or we don't necessarily know what the functions are, or we can look at two functions that we're very familiar with because we're not familiar with that exact function and we want to know to figure out what the limit would be. So the common ones like this would be sine and cosine, things that we can get without using our graphing calculator to find the limit of. So what it's saying here is that if I know the limit as x approaches a number of g and that equals the same as the limit as x approaches a value at h, then the limit as x approaches the one in between, the f function, which is in between the g and the h function, would also have the same limit. So again, very simple idea, just using an estimate really here to figure out what's in between the other two functions limit-wise to find the other limit. And that's all for our lesson.